Okay, hello everyone. And this video we are going to talk about doing a more complete calculation of work. Okay, because in the last video we demonstrate how to use the dot product to calculate the work. Okay, but sometimes will face a more difficult situation. That means your force is varying. Okay, the force is varying. Your force could be varying along the displacement direction. That happens a lot. So how to deal with this true situation? So we need to use the calculation skill called integration. So the first of all, how the force varies with displacement? Okay. A very simple example is the spring. Yeah, spring. The most simple example. Yeah, when you're pulling up the spring, when you're pulling further away from equilibrium position, you will feel stronger resistance, right? Okay, you pouring very away from the equilibrium position, you feel a very strong resistance. But as you if you're just pulling the spring a slight distance from minute distance from equilibrium position, you feel less resistance. So spring in this case, yeah, its force is varying. Its force is a function of displacement vectors. Okay, so this is the most simple example of varying force, but actually in physics we have lots. We will face this situation a lot. Your force most of the time, your force is a function of the position and displacement vector. Okay, let's go back to the first slide here. So, how do we calculate the work by varying force? Okay, so this is a picture here. Suppose we have a force is a function of x. Okay, if we want to calculate a work done by this force between x1 x2, how do we calculate that? Okay, so by doing this, we have to slice the system. We just add the work piece by piece. Okay, what does that mean? We want to calculate the total work between x1 and x2. What we have to do is we calculate the work piece by piece. Okay, I equal to 1 to n wi. Okay, and approach to, yeah, maybe infinity. Sorry. I maybe we start from, okay, for example, mm, okay, from xi to x2, maybe it is not accurate. Okay, so but just know it's just for explanation. Okay, okay. So we want to, when you can calculate the work done by varying force, we don't do it as a whole. So we just slice the system like this. Okay, we just slice this. If this is delta x, this is delta x, and this is another delta x. This is another delta x. Okay, we just slice the system, and we just calculate the work at a very small interval. Okay, we calculate work at a very small interval. So this is the work in the small interval, interval. So you will see here the work in a small interval is the f of xi times delta x. Yeah. Suppose we have this is f of xi. Okay. We do a very slice piece here, and f of xi is the force and times the very small displacement delta x. So that is a work in this small interval. And we do the same thing, we calculate the small work done on the next interval. When we keep doing this, yeah, we keep doing this, and every slide is always, and every interval is all delta x. every interval is O delta x. Okay, we just keep the interval the same. Yeah, it's not really, I cannot draw it very accurate. Okay, then wait for me. Wait for me. Yeah, this is a goofing here. Mhm. Here. And this also corresponding to f of xi. F of xi. Okay. So we just add a very small work together and doing a summation of them. And after all, we will get the total work done by this force. Total work done by this force. So the work is equal to summation I f of xi times delta x. Okay, this is the expression. Okay, so if you learn, yeah, you will learn this eventually in calculus class. If the delta x is equal to approach to zero, delta x approach to zero. Okay, that means very small interval. Okay, this is the definition of the. Uh, 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 yeah, I forgot one thing. This is force. This is force xi times delta x. Okay, this will become the integration of f of x and dx. Okay, and we have a range from x1 to x2. So that's the original definition of integration. The original definition of the integration is, yeah, he just want to trying to calculate the area under the curve. You see, when you add this piece together between x1 and x2, we add this very slight piece of work. That means small piece of area because f of xi times delta x is just equal to the area in this slice, in this small piece. Okay, and we add this small piece together between from x1 to x2. Eventually, it will become the area under the curve. Area under the curve. Okay, so calculating the work. So calculating the work by a variant force, it just the calculate the area under the curve. Okay, under the force curve. Calculate area under the force curve. Under the force curve. Okay, I just said area under the force curve. Okay, and calculate area under the force curve. Okay, so and it's which is equal to doing the integration of f of x force function with integration of force function with respect to dx from x1 to x2. Okay, so calculating the work done by variant force related to the integration in calculus. Okay, but in fact, Newton invent calculus to solve the physics problem. Yeah, you have to understand this. So it's hard to separate the calculus and physics. Okay, because Newton invent calculus to solve physics problem. That's why he invent derivative and integration. Yeah, derivative and integration. Newton invent these two mathematical skills to solve the physics problem. So you have to understand this. Okay, so this integrate and in this course, I won't spend much time on integration. To show you how to do the integration, I will I'll just show you some integration formula of power function. Okay, and then demonstrate the integration demonstrate how integration process by using this integration rule. Okay, because this is not calculus class. Okay, the calculus class should done more demonstration than me on this. Okay, so what else on this slide? Okay, calculate area under the force curve, and this slide is just what I just say. Okay, by calculating the work on the by a variant force, you just adding the work in a small period or small, yeah, small displacement. the work done on this small displacement and add them together, and eventually you will get the total work done by the variant force. So it's equal to force under the area under the force curves. Okay, so in this video, I'm going to show you a very simple example. So this is a variant force. Okay, this is a simple example. This force is a variant. Okay, from 0 to 6, between 0 and 4, the force is constant. Okay, that's okay. But between the distance the distance from 4 to 6, the force varying from the 5 to 0. And he want to try to calculate what's the work done by this force. Okay, and from this force curve, yeah, it's very simple curve. Okay, so we may not have to use the integration. Okay, we can use the concept is work is equal to area under the curve, area under the force curve. Okay. So this simple example, I just do this simple example. Okay, work. Okay, what's the more general description of work? Is area under the force curve, area under the force curve. Okay. Okay, that's okay. Let's calculate area on the force curve. So in this curve, yeah, we can we can split this curve by at this point at x equals 4. So this part is rectangular. So this part is triangle. This is triangle. Okay, so what's the area? How to calculate area of rectangular shape? I think it's very simple. So it's 5 times 4. Okay, and that's what's the area of the triangle. I believe all of you can understand this. 1/2 is 5 times 6 minus 6. Okay, so 20 plus 1/2, 1 times 2, so it becomes 25. So this variant force, he is doing 25 joule work from 0 to 6 meters. Okay, so area on the curve, that's very simple. I believe I have one homework is very similar to this problem. Okay, so area on the curve, because the shape of the curve is very simple, so you can use this concept to calculate the work done by a variant force. But for the next example from the textbook, this example is from textbook is 6.5, and for this problem you cannot use the it's very difficult for you to use just calculate just calculate area under the curve. You have to use the integration. Okay, because here this problem is its force function is more complicated. So it's very difficult for you to just calculate area under the curve. You must have used the integration. Okay, so I will do this example in the next video. Okay, I won't demonstrate this problem in this video. Okay, so what else? Yeah, I kind of forgot to list. Okay, area under curve. Okay, how to calculate the work done on the spring. Okay, area under curve, because this is a Hooke's law, right? Okay, I should mention this. Sorry, I forgot this, but it's very simple. So just use 1 minute to explain this. Like, because in Hooke's law, F is equal to kx, right? F is equal to kx. So if you draw the force as a function of x, it's this straight line. Okay, F is this is a force is this is curve. This is expressed by this curve. Force is a function of x. So if we want to calculate the force, if I can calculate the force between 0 and x, so what will we do? Okay, and this force is variant. So let's use the integration. Yeah, I should do this before talking about the simple example. Okay, F doing integration of force function with respect to x, and for here, if you want to try to calculate the work walk them from 0 to x. So you have the range 0 to x. So this will be kx dx. Okay. So for the integration, the constant can factor out. So you will have x dx. And how to do the integration of the power function? Yeah, I just show you the integration of the power function. You just know this is the rule for power integration of the power function. So it's from x1 to x2. Let's do this. Okay, the rule is it's become n plus 1, 1 over n plus 1, and x2 n plus 1 minus x1 n plus 1. Okay, this is a rule for power function integration. Yeah, if you don't understand right now, you just memorize it. Yeah, because eventually you will learn this in calculus class. And here, I don't want to explain that much. Let's just use this, okay? So for this integration, so x is power 1. Yeah, this x means x to the power 1. Okay, so it means n equal to 1. So we just leave this constant. So n is equal to 1, and the integration of x respect to x is 1 over n plus 1, and x2 is x. Okay, x2 is x, so it's x and 1 plus 1 minus the initial position is x1. So the initial position here is 0, so it's 0, 1 plus 1. Okay, so after all, you will get 1 over 2 x squared. So what if I change the range? If I change the range from maybe not from 0, from x1 to x2, what the answer will be? If I start from x1 to x2 and force the x, so what the answer would be? Okay, I hope you might already guess obtain the answers. So it's x1, x2, x dx. So let's apply the integration rule again. N equals to 1, so it's equal to 1 over 2, 1 over n plus 1 plus 1, and x2 n plus 1 minus 1 plus 1 minus x1 1 plus 1. Okay, so it will become 1 over 2 k x2 square. Yeah, minus x1 square. Okay, so that's a simple integration rule. I hope you can remember it. Okay, it's not that it's very easy to memorize this. Okay, this is the most simple integration. Believe me, there will be more difficult integration in calculus class. This is the most simple one, so it's not that hard. Don't scare yourself. Okay, when we use the integration for this example, is 1 over 2 x squared, and it is equal to the area under the curve. Okay, because this curve is very simple, so you can use the direct calculate area on the curve because the curve is simple. So it's Hooke's law, F equal to k delta x. So the x corresponding to the force called kx. So the area of under the curve is this triangle. So it's kx. This is kx, so it's x. So area is 1 over 2 x kx times x. So it's 1 over 2 kx squared. It's equal to the integration. It must be equal to. Okay, it must be equal to. Okay, so I just stopped the video here. I will demonstrate another more complicated problem in example 6.5. So see you in the next video. Okay, bye bye. Bye 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 bye.